So now that we've talked a bit about this kind of intuitive definition of a limit, what I now want to talk about is I want to talk about what we might call a more precise definition of a limit, an analytical definition of a limit. Um, and this is where we really start to get into the mathematics, like really deep into mathematics, um, because this is the first opportunity for us to really talk about proof and to talk about really strict definitions. So let's suppose that we wanted to find the limit that x as x approaches 3 of x plus 5. And so by substitution, we know that the limit as x approaches 3 of x plus 5 is going to equal 8. Okay, simple. You plug in 3, 3 plus 5 is 8. Simple, right? But from the perspective of mathematics, that's just not enough. So mathematics is about precision and it is about proof. And so we're going to use an analytic definition of the limit to prove that a limit actually does or does not have the values that we estimate or that we believe. Okay, so that's our goal inside of doing this, and this is to really introduce you to what the real analysis of calculus, all right, which can be very, very challenging, right? So we're going to spend a little bit of time doing this and a little bit of time talking about this definition and how we utilize this definition in order to better understand what it means to have a limit. So this is the precise definition of a limit. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x approaches a is L, and we write limit as x approaches a, f of x equals L, if for every epsilon greater than 0, there exists a delta greater than 0, such that 0 is less than the absolute value of x minus a less than delta, then f of x minus L in absolute value is less than epsilon. Okay, there's a lot sitting there, all right? So there are several things. We're going to go over and talk about what does this exactly mean and then how is it that we're going to use it. But, here's something that you must do. You must memorize this. That is a requirement. Memorize. You need to memorize it because the fact of the matter is that that's what we've got to do when we do math, right? It's really handy to be able to like Google things and to look things up and to look them up in our textbooks, and sometimes that can be really handy. But sometimes we simply just need to know things, and we needed to know them by heart. We need to know them memorized because we use them, okay, and we need to kind of internalize them in order to understand their nuance. And so this is the first one where you're going to sit down and you're going to memorize the precise definition of the limit. Okay? It's absolutely necessary. The second thing is this is the kind of thing that you should write down. It's a good way to memorize things is to write them down. You don't have to write them down over and over and over again, right? But at least write them down a couple of times or write this one down at least once as you're going through and writing notes for this particular video. Okay? So you are going to memorize, you're going to write this down because we are going to use it. Okay? And the best way that I found to be able to utilize definitions is to really know them. And the best way to really know them well is to be able to write them. Okay? So let's take a look at this precise definition now. And what we're going to do is we're going to utilize our example there, right? X plus 5, in order to, and looking at it, the limit as x approaches 3 for x plus 5. And we're going to use that in order to understand this precise definition of a limit. Okay? So what I'm going to do is I'm going to imagine I've got my function. I'm going to draw it on the Cartesian plane. Okay? Now we don't necessarily have to do this, but it's a really great way of illustrating what it is that's going on inside of this definition. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And I'm going to draw x plus 5. So this is 1, 2, 3, 4, 5. And down 1, over 1. All right, down 1. All right, over 1, up 1. Excuse me. So there's my function. This is f. F of x equals x plus 5. All right. Actually, what we're looking at is we're looking at x plus 3. All right, so that's f of x equals x plus 5. And we're going to be looking for the limit as x approaches 3 of f of x, our x plus 5. So let's look at this definition. Let f be a function defined on some open interval that contains the number a. Now, what we mean by an open interval is we mean that around the value a. So in this case, a equals 3. Okay, that's a right there inside of that definition of a limit. You can see a right here as well inside of that. Limit as x approaches a of f of x equals L. So that's around 3, and that's x equals 3, so that's going to be on the x-axis. Okay, so around an open interval. All an open interval means is it means some region around this value. Okay, and generally we put them in as parentheses. So let's say, for example, I'm going to go around this open interval here. Okay, or why don't we actually, just so that it has greater precision, we're going to do around the open interval here that we'll define is 2 to 4. Okay, so we'll put 1 on either side. Now, the fact is that we don't actually need it to be that big. We can make it smaller and smaller and smaller and smaller. In the analytic definition, it's any open interval, as long as it contains a. So, and that when we say open, it means that there's a little bit of wiggle room on either side of it, right? So we've got, in this case, we've got a full 1 on either side. We got an amount of 1 on either side, okay? Right, that's our open interval. So we say, okay, let's say that's the one that we want to look at. All right. Now the other thing here is except possibly at a itself. And so what this does is this allows us to say, well, what if it is the case that we don't have the function defined at a? We saw several limits where the function actually is not defined at a, right? But we still have a limit, right? We might have a hole or we might have an asymptote, okay? But it's not actually defined at a, right? So we don't actually need that. Now, then we say that the limit of f of x as x approaches a is L. So this is the thing that we're defining, okay? And this is how we talk about it. The limit as x approaches a, so as x gets closer to a, of f of x equals L. Great. So we've seen that several times before. That's our notation, right? And now what we're going to do is what's immediately going to follow is what that means, okay? So we need a to be defined on an open interval, okay, except at maybe a, right? It could be defined at a, but maybe not a, all right? And now we're going to say the limit is this thing. As long as we have those requirements, this is what we have. If for every epsilon greater than 0, okay, so epsilon, this thing here, stands for epsilon. There exists a delta greater than 0, and that's delta. And these are both Greek, okay? Notice epsilon is some non-negative number, okay? Non-negative number. There exists a delta greater than 0 such that if 0 is less than x minus a, which is less than delta, then f of x minus L is less than epsilon, okay? Now, let's go over a couple things first, all right? So the first thing to get here is that when I put, now from an analytic standpoint, when I put absolute values, so like I have x minus a, what I'm talking about is the distance from any x value, okay? X along the x-axis, all right? The distance from any x value to a, in this case like 3, okay, is going to be less than delta, right? So less than delta. And so what that means is that the distance from x, right, okay, right, here's a equals 3, and here's anything on the x-axis, right? What I want to know, here's like a delta distance, okay, and here's a delta distance on the other side, right? That's why we have the absolute value, is so that we can actually have the delta on both sides, okay? So like delta here is a distance, and that's an important fact to remember, okay? Delta is a distance. And it's the distance that all of our x values are away from A. So that's what we're saying. We're saying, what are the distances that, pardon me, what are the possible distances that x can be away from A? Okay, any x that I choose. X is a variable, A is a set point, right? So we could have it be 3.1. We could have it be 2.9. We could have x equal 2.88. We could have x equal 3.12, right? Depending upon what our delta is, okay? So like all the x values that are going to be around, right, around A. Then this other part is f of x minus L is less than epsilon, okay? Well, our L here, okay, if you remember, the limit as x approaches f of x is going to equal 8. That's what we're positing. So our L here is 8, right? Okay. When x is equal to 3, f of x equals 8. Okay, so here's f of x equals 8, right? And that's our L, yes? And the f of x values are now all the different y values that we could have in between, you know, for the function and 8, okay? So here, right, what I want to do here is I've got epsilon here is now these distances, okay? So the distances on the y-axis are going to be my epsilons, okay? And let's just imagine that they're the same size, okay? So this is, right, the distance between L equal to 8, okay, and a bunch of different f of x's, right? It could be f of x equals 8.7. It could be f of x equals 8.9, okay? It doesn't really matter, right? What matters is that if for any one that I choose, right, okay, any one that I choose in this region, right, I'm going to get back some delta over here in this region, right? Now here's the thing. It's a deep, deep thought, okay? Talked a little bit about mathematics as a philosophy. Mathematics is the deepest philosophy. Mathematics, we do profound stuff. This is not easy. You have to sit there and think about it for a little bit. You gotta sit there and go, huh, what is he talking about there? You might even pause it. Pause the video and go, what are the deltas? Because honestly, I can't say it any different way. I can't say it any different way. This is what it's actually stated. We'll see examples, you'll do examples, but sometimes you just need to sit there and think about it. Okay? All right, let's move on. All right. So now we've got these epsilons, and so I'm just going to say, okay, well, so what do I do with epsilon? What do I do with delta? So my epsilons are distances around y's, and my deltas are my distances around x's. Okay? All right. What do I do with that? Now, if you look here, this says if for every epsilon greater than 0. So I've now got every epsilon greater than 0. Huh. So what that means to me as a mathematician is that says if I have epsilon, okay, and epsilon, I'm going to pick any epsilon that I want. Doesn't matter what it is, okay? So I could pick any distance here, right? I could make epsilon equal to 0.5. And if epsilon is equal to 0.5, what that's going to give me is that's going to give me from 8.5 to 9.5. Okay? That's the distance because we got a 0.5 around 8. 8 is in the middle, 8.5 to 9.5. I could pick epsilon equal to 0.1, and that would give me 8.1, or excuse me, 8.9 to 9.1. And that's an epsilon of 0.1, right? It's a very small distance, okay? So if you remember, right, that's like that's going to be the values that you end up getting for your like your f of x. Okay? So any one that I choose, any interval of that size that I can choose, what it's going to give me back is it's going to give me back a delta. It's going to give me back a delta that I can use, right? So there exists a delta greater than 0. So I'll get one back, right? That makes this then true. Okay? That then makes this part true. Again, deep thought, right? But let's look at this. Let's say, okay, so let's say, for example, um, if, well, actually, let me hold on. Let me put up another page, okay? And then we'll actually do one with an actual example. We'll do one with two examples, okay? So let's take a look at what this means. We'll start out with this idea. First, what we're going to do is we're going to pick an epsilon, right? So for every epsilon, right? So epsilon, I'm going to use epsilon equals to 1. So I'm just going to utilize that value here as part of my example. So if epsilon equals 1, okay, then we want to be able to find a delta such that if we pick any f of x value, right, within the epsilon, we'll get back something that's within that delta range, okay? Now, we just pick our epsilon. So epsilon equals 1 means that I'm going to go from, right, okay? And so, like, just let me remind you, its limit as x approaches 3 of f of x equals 8. So our L is equal to 8, okay? So we've got, excuse me, this equals L. So I've got the absolute value is greater than 0, f of x minus 8, okay, is less than, excuse me, is less than 1. Okay, so 0 less than f of x minus 8 is less than 1. All right, just to go back and show you exactly what that looks like or why we have that, okay, it's that part of the definition right here. F of x minus L is less than epsilon. All right, so now what I'm going to do is I'm actually going to draw in, okay, here's actually, there's my 9, and then here's the one for 7, okay, right? And so this is the distance epsilon equals 1. And this is the distance epsilon equals 1. Okay, so I've got epsilon equals 1 on both sides. Now, what I'm going to do is I now need to find a delta. So I said for epsilon equals 1, we have 0 is less than f of x minus 8 is less than 1. That's this drawing right here. That goes from 7 to 9. Okay, 7 being on the lower end, 9 being on the upper end of the difference of 1. Right, now we want to find there exists delta greater than 0, okay? And this one's going to now be in the x's such that x minus, and in this case 3, is less than delta, right? Greater than 0, but less than delta. So I'll just draw down onto my x's, okay? There it goes to 2, right? And then we know that x plus 9 is going to go out to 4, okay? So that's my delta right here. Right? Now, we'll call this one delta 1, and we'll call this one delta 2. All right? In this case, in this one, because it's linear, what we have is that delta 1 and delta 2 are exactly the same size. All right? But they're not always going to be the same size, and we'll see some examples in which that's the case. What we want to get here in particular is we want to say, okay, so I've got these two deltas, right? And as long as I'm within this region between 2 and 4 on the x-axis, I'm going to get something between 7 and 9 on the y-axis. Okay, so as long as I'm between 2 and 4 on the x-axis, I'll get something between 7 and 9 on the y-axis, right? So what that's saying is that if my epsilon is 1, okay, then I just need somewhere between, right, this region right here, okay? The delta that I'm going to choose is I'm going to choose whichever is larger. Let's forget that. Whichever is larger, right? Because the larger delta is going to allow us to encompass everything. Whichever is larger, emphasize again, larger. I'll see if I can actually delete that out, okay? Whichever is larger, delta 1 or delta 2, okay? Because the larger area is going to encompass, like if delta 1 was bigger, then delta 2 would be inside of delta 1, right? Because it would be smaller than delta 1, right? So we're going to pick whichever one is larger. In this case, they're the same size. right? So delta equals 1. Exactly the same size. Okay? Now, we can choose it for different sizes too. So let's see what happens if we choose it for a different size. So now let's pick epsilon equal to 0.1. So this is now a smaller region, epsilon equal to 0.1. Okay? And so we want to say, well, we still have that the limit as x approaches 3 of x plus 5 is equal to 8. So we're going to get 0 less than f of x minus 8, okay, is less than 0.1. So what that's going to give me is that's going to give me a region 0.1 around 8. So that's going to be 7.9 to 8.1, right? So we'll just write this as an open interval, 7.9 to 8.1. Now, I'm just basically going to go over and I'm going to see, okay, well, there's that value here, okay? That's what f of x equals 8.1, and here's f of x equals 7.9. And so that's the open interval around 8. And then I can just go down to x, because my x's are now going to be my delta values. Okay? So there's my delta values, and my picture isn't all that great. Turns out they're exactly the same size. All right? So this is going to be, we'll call that delta 1. We'll call this one delta 2. Okay? And what we can see is that 3, right, we can find a delta around 3. Okay? That's going to give me every value, right, between 7.9 and 8.1. Right? There's some region around there that's actually going to allow us to do that. And so it's going to be our delta, right? We're going to have 0 less than x minus 3 is less than, and then it's going to be our delta, and delta is whichever is larger, delta 1 or delta 2. In this case, right, okay, what we're going to see is you can see that right down here, this is going to be 2.9, okay, and this one here is going to end up being 3.1 because we're perfectly linear. And we'll actually do an example of this where we actually do some calculation with this as well, okay? So this delta equals 0.1, right? Because 3.1 minus 3 is 0.1, and 3 minus 2.9 is 0.1, okay? So if epsilon is 0.1, right? If our f of x's are 0.1 around 8, then what we're going to get back, okay, is a delta that is within 0.1 of 3, okay? Let's do an analytical or an algebraic example of this to kind of give you a sense of how this is working algebraically, okay? And we know that the limit as x approaches 4 of f of x is going to equal 16, right? Remember that since x squared is a polynomial, you can just actually directly substitute, and it'll actually give you the value that you want here. Okay, it'll give you your limit. What we're going to do is we're going to say, suppose that epsilon equals 0.1. What is the value for delta that will prove the precise definition of the limit? Okay, that will actually allow us, right, to say that the precise definition of the limit gives us a true statement, that this is in fact the limit, okay? So if you remember back to what we were doing, right, with the graphs, what we did first was we looked at the f of x's, okay, right? We've got this statement, 0 less than f of x minus, in this case, 16, right, because that's our limit, that's L, is less than, in this case, 0.1, okay? So we're looking for an interval around, an interval of, 15.9 to 16.1. That's adding 0.1 to both sides of 16. Okay, so we've got an open interval of 15.9 to 16.1. All right. Now, what we're going to need to do is we're going to need to define what are the x's that give us 15.1 or 15.9 and 16.1, right? So we have f of x equals 15.9, and we have f of x equals 16.1. This means that x squared, okay, will equal 15.9, or x1 squared will equal 15.9, and x2 squared will equal 16.1. So the bottom end of our open interval, x1, is going to equal 3.9875 when I go out to 4 decimal places, and x2 will equal 4.0125. Okay? Now, delta 1 is the distance between x1 and, in this case, a and 4. Okay? And delta 2 is the distance between x2 and 4. So delta 1 is going to equal, okay, 4 minus 3.9875, which is 0.0125. And delta 2 is going to equal 4.0125 minus 4. So delta 2 is also going to be 0.0125. Okay, remember these are in absolute values. Okay, so we basically want to know, right, how big is delta? Then we choose the larger delta, which is in this case either one. Although technically, if you went down to more than 4 decimal places, you went down to like 5 decimal places, you'd start to see that that the second one is actually the larger delta. Okay, we choose the larger delta, which is going to equal, in our case, is going to be 0.0125. And so delta equals 0.0125. Okay. What you'll see sometimes if you're like reading on the internet or inside of our book is you'll see the max, right? It'll say the max of delta 1, delta 2, right? Which just means whichever is larger. Okay, so whichever is the larger value. All right, so suppose that epsilon, we're going to say, in this case, we're going to figure out what our epsilon is, and we're going to create the open interval around our limit, okay, around L. So in this case, that ended up being 15.9 to 16.1, all right? And then what we want to do is we want to determine what are the x's that give us back 15.9 and 16.1, okay? So f of x equals 15.9 and f of x equals 16.1. Then what we're going to do is go solve for x. So we're going to go backwards solving for x, right? Okay, and that'll give us an x1 and x2, right? That's going to be the boundary on either side, right? That's going to be the boundary on either side of our value a, okay? The value that we have for the limit, right? So we're going to choose whichever one of those is larger, and whichever one of those is larger is going to be our delta, our selected delta, okay? And then that will actually, prove the statement, okay? That'll actually say, you know what, this is in fact the case. This is true. Let's take the same example and actually let's look at one where it doesn't actually have the same exact value, okay? So we'll use f of x equals x squared again, okay? And we'll use, again, we want to know the limit that as x approaches 4 of f of x, and we know that equals 16, but let's instead use epsilon equals 1, okay? This will give us a different set of values. So now epsilon equals 1, we've got 0 less than f of x minus 16, okay, is less than 1. So that's an open interval of 15 to 17. Okay, so 15 to 17. All right. So what we're going to do is we're going to set f of x1 equal to 15 and f of x2 equal to 17. All right. And so consequently, that gives me that x1 will equal 3.873, and then x2 will equal 4.1231. Okay. Now we're going to go find our deltas based upon x1. Okay. So remember that we have 0 less than x minus 3, which is less than delta. All right. So our delta 1 is going to equal 3 minus 3.873, right? Because we need to get the absolute value. All right. So, or excuse me, 3.873 minus 3, which is going to be 0.873. Then delta 2 is going to equal 4.1231 minus 3, which is going to equal 1.1231. Now what we have is we actually have two different deltas. So it's going to matter that when we say, okay, we want the max of delta 1, delta 2, we want whichever one's bigger, the maximum. And so that's going to equal, that's delta, equals the max of those two. It'll equal 1.1231. So that's what our delta is. So if epsilon equals 1, then delta equals 1.1231, okay? And we can in fact say that if f of x minus 16 is less than 1, then x minus 3 is less than 1.1231. Okay? And in fact, this is true. We just proved it. We just proved that that was in fact going to be the case. Notice, here's our precise definitions of the limit, right? If epsilon is equal to 1, then delta equals 1.231. And so if f of x minus 16 is less than 1, then x minus 3 is less than 1.1231. Okay? And it actually allows us to prove that if we have this particular epsilon, then we're going to have this particular delta. Okay? So in our next video, what I'm going to do is I'm then going to show you how it is that we're going to use this analytic definition to prove for every epsilon, not just if we prove for one epsilon, but if for any epsilon, okay, that we choose, that there exists a delta, right, such that f of x minus L less than epsilon gives me x minus A is less than delta. Okay? All right. So spend some time with this one. It's a deep thoughts going on here. All right? Tough stuff. We spent a lot of time on this when I was in my undergraduate analysis class. Okay, on to the next.